All right, everyone. Today we're going to talk about heat and temperature. Before we really can talk about heat and temperature, though, we have to talk about matter. All right, we're finally to the main event, heat versus temperature. What in the world is the difference between heat and temperature? Aren't they the same thing? If something's hot, doesn't it have a high temperature? It doesn't quite work that way in chemistry, guys. Heat is the flow of energy due to a temperature difference. Heat moves from hot things to cold things. It's kind of like osmosis, where something moves from a higher concentration to a lower concentration. Heat flows from a hot item to a cold item. It's an energy movement. There are two different kinds of processes that involve heat. They are exothermic and endothermic processes. And both exo and endothermic processes can be either physical or chemical. If you think back to biology, endo and exo are prefixes again. Exo means outer, so here energy is being released. Endo means inward. Energy is being absorbed in an endothermic process. You've heard these terms before in terms of skeletons. Crustaceans have exoskeletons and humans have endoskeletons. Let's take a look at the diagram to make sure we understand exothermic processes versus endothermic processes. In the beaker with the red liquid, obviously red is meaning hot, this is an exothermic process. The energy coming from the hot liquid is going out here, outward. You can feel the heat coming out. The glass may get hot. That energy goes outward. When something is cold, it's taking the energy from its surroundings to try to warm up, and the glass will feel cold to you. That's heat. Temperature, on the other hand, is simply a measure of kinetic energy in the molecules of a substance. So when you stick a thermometer in a liquid and you're measuring its temperature, the higher the temperature, the faster the particles in that liquid are moving. That is what temperature is. In the last slide, we looked at heat and we realized that heat was the transfer of energy typically from one warm object to a cooler object, kind of like osmosis. But we didn't define energy, so now we have to look at energy. Energy is the capacity to do work. Capacity in this instance means the ability. Therefore, energy is the ability to do work. There are several different forms of energy. Energy can be either kinetic or potential. If it's kinetic, we have various forms of kinetic energy: thermal, mechanical, electrical, magnetic. Potential energy is stored energy, and that can come in the form of chemical, elastic, nuclear, or gravitational. We can also experience energy in terms of sound or light energy. All energy is conserved. The law of conservation of energy tells us that energy cannot be created or destroyed, it gets transferred. So of these forms of energy here on the slide, energy gets transferred from one form to another. Please take a moment to copy down the different forms of energy available to us, as you will need the different forms in order to solve some problems. We can measure changes in energy, and we're going to get into that in this slide. Before we do that, however, we need to take a look at something called specific heat. different substances absorb and retain energy in the form of heat in different amounts. We can use specific heat to identify an unknown object. Specific heat, by definition, is the amount of heat required to change the temperature of 1 gram of a substance by 1 degree Celsius. We represent specific heat as a lowercase s. Now you might wonder, what does all of that mean? Well, let's take a look at Lake Michigan for a second. Sorry about that. Let's take a look at Lake Michigan. It is one of the largest bodies of water around Calumet City and Chicago. Chicago is a lakeshore town. If you've ever noticed the meteorologist on the news talking about the temperatures being lower at the lake than they are in the suburbs during the summertime and warmer at the lake during the wintertime than the suburbs, the reason for this is specific heat. During the summertime, although the air is quite warm, Lake Michigan greedily absorbs all of the heat energy from the air during the summertime, and that keeps the temperatures cooler in the city than the suburbs. During the wintertime, all of that heat energy gets released back into the air, the lake cools back down, but it keeps the city a little warmer than the suburbs. Pay attention to this the next time you see a meteorologist talking about the weather and the temperatures specifically of the city and the suburbs. Let me put that back. Now, the SI unit for energy is the joule, and the specific heat of water is the largest we know, and it is 4.184 joules per grams degrees Celsius. We can measure the energy change in a substance with the following equation, Q equals Sm delta T. Now, Q stands for energy. S stands for specific heat. We just learned about that. M, what do you think it stands for? Mass, exactly. And this must be in grams. And delta T, any ideas? You got it. It's the change in temperature. You have to subtract the initial from the final. So it's always final minus initial temperature. The reason for this is because if we have an endothermic process, energy is going into the substance, which means it gains energy, and energy will be positive. If the substance is experiencing an exothermic process, such as cooling, then the energy will be negative. And the reason for that is the delta T, the delta temperature, would be a negative value. Let's take a look at an example in our last slide for today. Here's a very basic example using the energy equation. We are told to measure the energy that will be required to heat 100 grams of water by 50 degrees Celsius. Whenever we work with algebra problems, we always want to make a list of everything we know. So I'm going to make a list over on the side of Q, S, M, and delta T. The problem tells us to measure the energy. So that means we don't know what energy is, so we don't know Q. That's our question mark. The problem also tells us that we have water. This allows us to use the specific heat of water, which is 4.184 joules per gram degrees Celsius. Each material has its own specific heat. The problem also tells us that we have a 100.0 gram sample, and it tells us the delta T is 50 degrees Celsius. Now, it did not tell us that it's cooling, and it did not give us a negative, so we use the positive delta T. We are ready to now look at our equation again, and then we're going to just simply plug and chug. So, let me change colors here. We know from the last slide that Q equals SM delta T is our equation for calculating energy. So we simply plug and chug our values. We get 4.184 joules per gram degree C times 100.0 grams. Let me move this over just a hair. Oh, it's all together, huh? We'll make it a little smaller. Move it over. Times 50 degrees C. Now let's see what cancels out. Our grams cancel out because these grams right here are in the denominator, and our degrees Celsius cancels out because degrees Celsius is in the denominator. We're left simply with joules, which is perfect because that's the SI unit for energy. When we run everything through our calculator, we get a calculator answer of 20,920 joules. But in looking at the problem, we can only keep two significant figures. So our reported answer is going to be 21,000 joules. Now you might be saying, Mrs. Smith, there was only one significant figure, but I want to quickly go back and add a decimal place right here on that 50. That way we have 2 instead of 1. Please make sure you copy down this entire example.